Hello everyone, my name is Wenbin Zhang. I'm recent graduate from University of Maryland, Baltimore County. This is John. Today I'm going to present our work FEAT, Fairness Enhancing and Concept Adapting Decision Classifier. This is John work with Albert Bifet. Uh, as you know, like AI assistant has been widely used in both online and as well offline settings to assist or even complete automate the decision making. Yet, these automated data-driven tools may, even in absent of intent, lead to a loss of fairness and accountability in the employed models. A plethora of such kinds of AI-based discriminatory incidents has been observed and reported in Amazon's hiring system case, for example, in which AI assistant's task was pre-screening and acceptance of applicants. Qualified female applicants were systematically underscored. Growing concern have therefore been raised regarding bias and discrimination of such systems. This growing concern our discriminative behavior AI models has motivated a number of approaches. Model of learn process data in offline settings, assuming the data is generated by a single concept without drift. Our methods focus on the online setting for data stream, where the data arises continuously and the underlying data distribution might also change over time. The existing AI fairness methods typically can be categorized into three main families. The first one, pre-processing approaches, and the second, in-processing approaches, and post-processing approaches based on whether they mitigate bias at the data level, the algorithm level, or the output of model, respectively. Representative works in the pre-processing approaches include massaging and reweighting, where the former directly swipe the class label of selected instance to change class data distribution, while later assigns different weights to different community to reduce discrimination. Among in-processing approaches, one of the recent work as a regularization turns to the mixed integer programming model to penalize discrimination. In case of post-processing, one work process with additional prediction threshold to work against bias, while the additional boundary of outputs is shifted with respect to fairness in the proposed work by Cardell et al. So fairness in data streams would require addressing of non-stational distribution known as the concept drift. The learning algorithm therefore should be able to remain stable on previous length and not outdated concepts while adapting to such drifts. The adaptation is typically enabled by learning incrementally from new instance and by forgetting outdated information from the model. A significant amount of work has been done with respect to this specific issue. However, the combined approach of addressing both fairness and concept drift has enjoyed relatively little research. Our work situates in this research direction to enable fairness-aware learning in non-stationary data stream. When learning in non-stationary data streams, uh, it brings unique challenges. First, discriminate-aware learning for such sort of application should be able to process instance on arrival without the need to storage and reprocessing. However, most of existing fairness approach assume the full data can be scanned for multiple times, which is infeasible for such type application. Second, different from the static fairness method assuming stationary data distribution by design, in online settings, the underlying data population might also evolve over time. So addressing both fairness and evolving distribution simultaneously is challenging as the non-stationary companies and complicated the bias decision region. In addition, transferring approaches among these domains is not straightforward. Sophisticated design is therefore expected. Uh, Up to now, more than 20 notions has been proposed to measure the discriminative behavior of AI models. One of the most widely used measure is the statistical parity, which examines whether the probability of being assigned a positive target class, for example, allocating health care resources, is the same for both privileged and unprivileged groups. Here we have the formulation here. So the D is it will be our data stream, and the PP and the PN will be referred to a privileged community receiving positive and classification, and the privileged community receive negative classification. So are the UP and UN for the unprivileged community. Here, the attributes that distinguish privileged group from unprivileged group is referred as sensitive attributes, with the sensitive value defining the unprivileged group. The aim of FairnessAware Learning is to train an updated decision model which provides accurate prediction, yet does not unduly bias against unprivileged groups. We built our model based on the vanilla Hofstede tree to mine a high-speed data string. Hofstede tree introduces a decision tree from a given string incrementally, briefly scanning each example in the string only once and stored sufficient information in its leaves in order to grow. Here, the static information will only stored in the leaves. For the already split nodes, it will not store the information anymore. So the crucial decisions are when and how to do the split by the Hofstede bound. However, such decisions are based on the information gain to optimize the predict performance, so they do not consider fairness. In addition, the construction of the tree also assumes the distribution generating example does not change over time. In this work, to enable fairness-aware learning and concurrently adapt to non-stationary data distribution, we extend the Hofstede tree model in two ways: by introducing an enhanced fair splitting criterion that enables the fairness-aware learning, and by adding the ability to detect and adapt to the evolution of underlying distribution. So to address the fairness-free issue of information gain, we'll first propose the FairnessEnhancing gain as follows. Pretty much this is the formula here. So for the where A is the attribute relative to the correct instance of the string stored in sufficient statics, the discrimination is calculated according to the previous introduced static parity. The idea of FairnessEnhancing gain aligns with the information gain, but focus on the discrimination, and is also the higher the model. However, FairnessEnhancing gain does not have the weighting factor. The rationale is to care for the local discrimination to maximize the cumulative fairness by assigning equal weights to different discriminatory representations. Specifically, each partition induced by the attribute A contributes equally to the cumulative fairness of A, regardless the number and the size of the branches. The FairnessEnhancing gain is then tied with information gain through multiplication as the FairnessEnhancing information gain. Multiplication is favored when combining them as a conjunctive objective. Our other operations, for example addition, as the value of these two matrices could be in different scale, and in order to promote fair splitting, which result in a reduction in the discrimination and after split, let's to say the FairnessEnhancing gain is a positive value. Here is the tree growing scenario for the Hofstede tree. As you can see on the stationary distribution, the tree will keep growing. So improves their performance will improve all the causal string as it generalizes better after incorporating more examples into the model. From the decision region perspective, its decision regions are further split to have more detailed decision regions. Compared with Hofstede tree, our model grows similarly but with different splitting criterion. So for us, we would create alternative subtrees when accuracy and fairness deteriorates. To do so, we first need to maintain sufficient statics in the non-leaf nodes. So also all the statics in the non-leaf node, and when the performance deteriorates, we'll try to have alternative tree here. So if it performs better than the original tree, it will be replaced here. Otherwise, if it does not compare better to the original branch, it will be pruned. For our FairnessAware system, we also have the null attributes. So which means not splitting is the splitting is at least better than not splitting, by considering the modality of a no split. So in our system, we need to calculate fair information gain fair enhancing information gain. So the current class distribution is used to represent information gain, and the fair enhancing gain is evaluated as the current level of discrimination. And we'll also keep track of sufficient static to calculate fairness of related statics. For the memory, additional memory compared with the Hofstadter tree will be like equal to two additional attributes for the fairness related information. And we also need to maintain all the number of nodes comparing to only the leaves in the Hofstadter tree. For the evaluation, we perform the performance of FEAT and other baseline are evaluated based on the prediction accuracy and the fairness performance, just as typical in the domain of FairnessAware Learning. We perform the sequential evaluation in which incoming instance first being predicted upon arrival, and it's available for model updates after the prediction. We render for the dataset, we consider two datasets, adult set and the census dataset, both aiming to predict whether the individual's annual income will exceed a certain amount. These two datasets are static by design. We render them as discriminated data stream by randomizing the order of the instance and processing them in sequence. For the baseline, we consider four types of directions. The first one, base model, which is the base model of our model. So the list will be fair splitting criterion from the Camillans. We also consider two more fairness online fairness method, FEAT and FEI. Or I also consider one more representative concept adapting learner, HAT. So from the results, it's clear that our model is able to diminish the discrimination to a lower level while maintaining fairly competitive accuracy. Since we propose a new splitting criteria, we would like to justify its theoretical design. So in here, we incorporate our new splitting criteria into the best baseline model, denoted as FAHAT plus, and we also use FEAT minus, representing the FEAT driven by FAHAT's splitting criteria. With all other components still the same to compare them respectively. From the table results shown here, it's clear that our new splitting criteria of the idea of learning to all groups being treated equally, therefore indeed push the discrimination to a lower level, which is consistent with its theoretical design. We also did another statistical experiment to verify that the enhanced anti-discrimination ability of our new splitting criterion is statistically significant. We further look at the Pearson correlation coefficient between sensitive attributes and decision boundary. As we can see, our splitting criteria-based method predict boundaries are less correlated with sensitive attributes than FAHAT due to its fairness enhancing ability. Our splitting criteria's learning idea of all groups being treated equally regardless of population size, therefore indeed further reduce the cumulative discrimination. So to sum up, for this paper, we focus on a highly underexplored discrimination conscious learning in the evolving data stream. To address this challenges, we propose FEAT with embedded fair enhancing splitting criterion and further equip it with the ability of change detection and the concept forgetting to handle discriminated and non-stationary data stream. The positive result of conducted experiments show the versatility of FEAT in the online setting. And that's all for my presentation. Please refer to our paper for more details, and thank you for your attention.